After analyzing every grain of the Bennu asteroid sample, NASA scientists have published their most significant findings yet in 2025. Among the discoveries, researchers identified 14 amino acids in the sample and achieved unprecedented precision in measuring the Yarkovsky effect on Bennu's orbit. The black dust mystery has been solved, the extra 60 grams of material explained, and the implications are staggering. These discoveries have led to refined orbital calculations that dramatically reduce uncertainty about what will happen when this potentially hazardous asteroid approaches Earth in 2135. But reaching these groundbreaking conclusions required an extraordinary scientific effort that pushed the boundaries of laboratory analysis, the 2-year analysis marathon. Scientists built semiconductor clean rooms and ran 24-hour shifts across institutes to preserve Bennu's dust, calibrating advanced imaging and chemical analysis techniques to probe 4.5 billion-year-old grains. The moment researchers received the 121.6 grams of Bennu material, they knew they faced an unprecedented challenge. This wasn't just another rock sample. This was material that had traveled through space since the solar system's formation, and every precaution had to be taken to preserve its pristine condition. Research teams immediately began constructing specialized clean rooms with air filtration systems more advanced than those used in semiconductor manufacturing. The contamination protocols they developed went far beyond standard laboratory practices because even a single speck of Earth dust could compromise decades of scientific work. The analysis required instruments that pushed the boundaries of current technology. Each technique required months of calibration and testing before scientists could trust the results they were seeing. Teams worked around the clock in carefully coordinated shifts. While one group examined particles under electron microscopes, another team prepared samples for chemical analysis, and a third group processed data from the previous day's experiments. The 24-hour schedule was necessary because the instruments required constant monitoring and the volume of material demanded this intensive approach. Every single grain had to be cataloged, photographed, and analyzed multiple times to ensure accuracy. The data output was staggering. Each particle generated thousands of data points, and with thousands of particles to examine, the computational requirements quickly exceeded what standard laboratory computers could handle. Scientists had to develop new algorithms just to organize and process the information they were collecting. The pattern recognition software needed to identify mineral types, organic compounds, and unusual features required machine learning approaches that hadn't been used in planetary science before. Multiple research institutions coordinated their efforts through shared databases and regular video conferences. Teams at NASA's Johnson Space Center worked alongside researchers at universities across the United States, while international partners in Japan, Europe, and Australia contributed specialized expertise. The collaboration involved 200 scientists from 35 institutions across 6 continents, each bringing unique capabilities to the analysis. Some institutions specialized in organic compound identification. Others focused on mineral analysis, and still others contributed expertise in isotopic measurements. The first major findings emerged in late 2024, but these were just preliminary results. Scientists published papers showing that Bennu contained far more complex chemistry than anyone had predicted. The mineral diversity exceeded expectations. Organic compounds appeared in unexpected concentrations, and water signatures were found throughout the sample. These initial discoveries hinted that the full analysis would reveal even more surprising findings, but researchers knew they needed additional time to verify their results. The original timeline called for a 1-year intensive analysis period, but the complexity of the sample forced scientists to extend their work well into 2025. Every time researchers thought they understood a particular aspect of the sample, they discovered new features that required additional investigation. Mineral grains that appeared simple under initial examination revealed complex internal structures when viewed with higher resolution techniques. Organic compounds that seemed familiar turned out to have isotopic signatures that challenged existing theories about their formation. International coordination became crucial as the analysis progressed. Samples were carefully divided and shipped to specialized laboratories around the world, with each institution contributing their particular expertise. Japanese researchers used advanced ion beam techniques to examine individual mineral grains. European teams applied cutting-edge organic analysis methods developed for studying meteorites. Australian scientists contributed expertise in shock metamorphism analysis. American laboratories coordinated the overall effort and maintained the master database of results. Quality control procedures required multiple independent measurements of every significant finding. When one laboratory identified an unusual organic compound, at least 2 other institutions had to confirm the discovery using different analytical techniques. This redundancy was essential because the implications of the findings were so significant that scientific credibility demanded absolute certainty. The peer review process for the resulting papers was more rigorous than typical because the discoveries challenged existing models of asteroid formation and evolution. The computational challenges grew as more data accumulated. Scientists needed supercomputer time to model the complex chemical processes that had occurred on Bennu's parent body. The simulations required to understand how organic compounds could survive for billions of years pushed computational chemistry's limits. Researchers developed new software tools specifically for asteroid sample analysis, tools that will likely be used for future sample return missions. By early 2025, the coordinated effort began producing peer-reviewed publications that painted a comprehensive picture of Bennu's composition and history. The findings exceeded all expectations in terms of scientific value. Each paper revealed new aspects of asteroid chemistry, from the preservation of organic molecules to the complex history of water-rock interactions. The sample provided insights not just into Bennu itself, but into the broader processes that shaped the early solar system. The methodical approach finally yielded results that justified the extensive time and resources invested in the analysis. Scientists published definitive explanations for mysteries that had puzzled them since the sample's return. The success of this analysis marathon established new standards for sample return mission protocols. Future missions to asteroids, comets, and other small bodies will benefit from the techniques developed during the Bennu analysis. The 2025 conclusions represented more than just scientific discovery. They demonstrated that methodical, careful analysis of extraterrestrial samples can yield insights that reshape our understanding of planetary formation, asteroid evolution, and the distribution of organic compounds throughout the solar system. The 2-year effort established Bennu as the most thoroughly studied asteroid in history, providing a baseline for understanding similar objects that pose potential threats to Earth. Yet among all the discoveries that emerged from this intensive analysis, one particular finding had puzzled researchers from the very beginning: solving the black dust mystery. When scientists lifted the lid on the OSIRIS-RX sample canister that September day in 2023, they expected to see clean electronics and organized sample containers. Instead, they found themselves staring at a fine coating of black dust scattered across the avionics deck and clinging to metal surfaces throughout the canister. This wasn't supposed to happen. The sample had been sealed in a secure container during the entire journey from Bennu back to Earth. So where did this mysterious dust come from? The answer lay in the violent physics of the sample collection event itself. A nitrogen jet shockwave blew fine Bennu dust back into tiny crevices of the canister, explaining the black coating. When OSIRIS-1 released high-pressure nitrogen gas onto Bennu's surface during the touch-and-go sample acquisition mechanism operation, the blast created much more dramatic effects than mission planners had anticipated. The nitrogen jet hit the asteroid's surface with tremendous force, creating a shockwave that propagated across the surrounding terrain and pulverized surface materials into particles much smaller than the rock fragments the collection mechanism was designed to capture. To confirm the dust's origin, researchers immediately began spectral analysis of the particles. They used infrared spectroscopy to identify the chemical signatures of the material, comparing them to known Earth minerals and spacecraft components. The results ruled out terrestrial contamination completely. The dust showed none of the chemical markers typical of Earth materials, and it didn't match any of the metals or composites used in the OSIRIS-RX spacecraft construction. Advanced chemical analysis techniques determined the exact composition of individual dust particles. Mass spectrometry broke down the particles into their constituent elements, while X-ray diffraction revealed their crystal structures. These tests produced a startling result. The dust contained identical isotopic signatures to the main Bennu sample. The ratios of different isotopes of carbon, nitrogen, and oxygen matched perfectly with the larger rock fragments collected from the asteroid's surface. The breakthrough came when researchers modeled the physics of the nitrogen gas blast in detail. The force was so intense that it broke down larger particles into microscopic dust, creating a cloud of fine material around the spacecraft. The pulverization process was more extensive than computer models had predicted because Bennu's surface turned out to be much looser and more fragile than scientists expected. The shock wave created during sample collection was powerful enough to affect surface materials across a much wider area than originally anticipated. Some of the pulverized particles found their way into the sample canister through gaps in the sealing mechanism that were too small to be detected before launch. These microscopic openings were within acceptable tolerances for the mission, but they provided pathways for the finest dust particles to enter the canister during the brief contact period. The violent disruption of Bennu's surface during the nitrogen blast created conditions that allowed these tiny particles to infiltrate areas of the spacecraft that mission planners thought were completely sealed. When scientists analyzed the composition of the dust particles in detail, they made another significant discovery. The dust came from Bennu's most ancient surface layers, representing material that had been exposed to space for millions of years. This meant the dust was potentially more scientifically valuable than some of the larger rock fragments in the main sample. The surface layers contained information about how cosmic radiation and micrometeorite impacts had affected Bennu over geological time. The dust particles also showed higher concentrations of certain minerals compared to the bulk sample. Olivine and pyroxene, two important silicate minerals, appeared in greater abundance in the dust than in the larger fragments. This difference suggested that the asteroid's surface had been sorted by size over time, with smaller particles of certain minerals accumulating in the uppermost layers while larger fragments of different compositions remained buried deeper. Advanced imaging techniques revealed that individual dust particles contained multiple mineral phases mixed together in complex patterns. Some particles showed evidence of thermal processing that occurred when Bennu's parent body was still hot, while others preserved signatures of cold formation processes in the outer solar system. This mixing indicated that Bennu's surface represented a complex blend of materials from different parts of its parent asteroid. The solution to the black dust mystery emerged through 2025 analysis that combined all these findings into a comprehensive explanation. The dust represented some of the most pristine material from Bennu's surface, material that had been pulverized by the spacecraft's nitrogen gas blast and transported into the canister through microscopic gaps in the sealing mechanism. Far from being contamination or an unwanted byproduct, the dust turned out to be an additional scientific treasure. The discovery changed how scientists viewed the sample collection process. The dust provided information about Bennu's surface composition that complemented the larger fragments in unexpected ways. It offered insights into space weathering processes, surface sorting mechanisms, and the preservation of ancient materials on asteroid surfaces. The mystery that initially puzzled researchers had transformed into a valuable source of scientific data. The black dust mystery's resolution also influenced planning for future sample return missions. Engineers now understand that shockwave effects during sample collection can transport fine particles in ways that weren't previously considered. Future spacecraft designs will need to account for these phenomena, either by preventing dust accumulation or by designing systems to capture and study it systematically. The dust analysis demonstrated that even unexpected discoveries can yield important scientific insights. What began as a puzzling contamination concern ended up providing researchers with additional windows into Bennu's composition and history. The 2025 findings showed that the mysterious black dust represented some of the most ancient and scientifically valuable material collected from the asteroid's surface. Yet the dust wasn't the only surprise waiting for scientists when they examined the sample canister's contents. The extra 100 grams explained. The 121.6 grams of material that scientists found in the sample canister represented a massive overdelivery compared to the mission's original target of 60 grams. This wasn't just a small miscalculation. The sample collection had yielded more than double what mission planners expected, and nobody could immediately explain where all this extra material had come from. The touch-and-go sample acquisition mechanism had performed exactly as designed during its brief. Contact with Bennu's surface, so the abundance of material suggested that collection processes beyond the primary mechanism had been operating simultaneously. Mission engineers had carefully calculated how much material the taxon system would collect based on laboratory tests and computer simulations. The cylindrical collection head was designed to capture particles smaller than 21 centimeters in diameter when pressed against the asteroid's surface. The nitrogen gas first would mobilize loose surface material and redirect it into the collection chamber, while contact pads on the collection head would gather small particles through direct contact. These calculations predicted a collection of approximately 60 grams, which would satisfy all mission science requirements. When scientists began analyzing individual particles from the sample, they discovered evidence that multiple collection processes had operated during the brief contact event. The primary taxon mechanism had indeed collected the expected amount of material, but several secondary processes had simultaneously gathered additional particles through mechanisms that hadn't been fully anticipated during mission planning. These secondary mechanisms included electrostatic attraction of fine particles to metal surfaces, Bohack mobilization of surface materials across a wider area than expected, passive debris capture as the spacecraft moved through loosened material, and the pulverizing blast effects that created more fine particles than predicted. The spacecraft's approach to Bennu created aerodynamic effects that mission planners hadn't fully considered. As OSIRIS-RX descended toward the surface, it pushed through the extremely thin atmosphere of gas and dust particles surrounding the asteroid. This movement created a bow shock wave that propagated ahead of the spacecraft, loosening surface materials across a much wider area than the taxon head would directly contact. The bow shock effect dislodged particles from regions several meters away from the actual contact point. The loosened material created by the bow shock formed a debris cloud that the spacecraft flew through during its approach and departure from the surface. Some of this material was captured through passive collection as particles simply collided with various parts of the spacecraft and stuck to its surfaces. The collection head, with its cylindrical shape and contact pads, acted like a particle trap as it moved through this debris field. Additional material accumulated on the head's exterior surfaces through these passive impacts. The nitrogen gas blast itself created more dramatic effects than computer models had predicted. When the high-pressure gas hit Bennu's surface, it didn't just mobilize the immediate contact area. The gas blast created pressure waves that propagated through the loose surface material, causing particles to become airborne across a much larger region. Some of this material was drawn back toward the collection head by the gas flow patterns, while other particles were captured as the spacecraft moved through the expanding debris cloud. Surface material turned out to be much looser and more easily mobilized than mission planners had anticipated based on telescopic observations and theoretical models. Bennu's surface regolith had a consistency more like loose gravel than consolidated rock, which meant that relatively small disturbances could mobilize large quantities of material. The combination of the bow shock, direct contact pressure, and nitrogen gas blast affected surface materials across an area much larger than the taxon head's contact footprint. When scientists examined the extra material in detail, they discovered it represented scientifically valuable samples from different layers of Bennu's surface composition. The passively collected particles included material from regions that the primary collection mechanism hadn't directly contacted, providing researchers with a broader sample of the asteroid's surface diversity. Some particles showed evidence of coming from deeper layers that had been excavated by the collection process, while others represented the uppermost surface materials that had been most exposed to space weathering. High-resolution imaging revealed that the sample contained larger rock fragments than the taxon mechanism was specifically designed to collect. Some particles exceeded the planned size limits, but had been captured anyway through the various secondary collection processes. These larger fragments provided insights into the internal structure of Bennu's surface materials and the mechanical properties of the asteroid's regolith. The size distribution of collected particles extended far beyond what mission planners had expected. The abundance of material created unprecedented research opportunities for scientists studying the sample. Instead of carefully rationing small quantities of material for different types of analysis, researchers could conduct multiple independent studies using different analytical techniques. The extra material allowed for destructive testing methods that wouldn't have been possible with a smaller sample, and it provided enough material for international collaboration with research institutions around the world. Particle analysis revealed that the different collection mechanisms had preferentially captured different types of material. The primary taxon system collected a representative sample of the contact area's composition, while the secondary processes gathered materials from a wider geographic area of Bennu's surface, providing insights into regional variations in surface composition. Some fragments appeared to have been freshly excavated from beneath Bennu's surface by the collection process, showing less space weathering than particles from the uppermost surface layers. The success of collecting so much extra material influenced planning for future asteroid sample return missions. Engineers now understand that surface interactions during sample collection can mobilize much more material than primary collection mechanisms are designed to capture. Future missions can take advantage of the secondary collection process by designing spacecraft systems to capture and organize the additional material rather than allowing it to escape. The extra 60 grams transformed the Bennu sample from a targeted collection into a comprehensive survey of the asteroid's surface materials. The unexpected abundance provided scientists with research opportunities that exceeded all original mission goals. But the real surprises were only beginning to emerge as researchers examined the sample's composition under high-powered microscopes. Water signatures beyond expectations. Spectroscopic analysis revealed hydrated minerals and concentrations that defied every prediction scientists had made about asteroid water content. The abundance of phyllosilicates throughout the material indicated that Bennu had experienced water interactions far more extensive than any asteroid sample previously studied. These weren't just trace amounts of water molecules trapped in crystal lattices. The sample contained clear evidence of prolonged water-rock interactions that had fundamentally altered the asteroid's composition over billions of years. Laboratory analysis identified hydrated minerals distributed throughout every particle examined from the sample. Phyllosilicates, which form when water chemically bonds with silicate minerals, appeared in concentrations that surprised researchers. These minerals require liquid water to form, indicating that Bennu's parent body once contained substantial amounts of liquid water that persisted long enough to alter rock compositions. The uniformity of hydration throughout the sample suggested that water-rock interactions occurred on a large scale within the parent asteroid rather than being localized to specific regions. Isotopic analysis of the water signatures provided crucial insights into the origin of water in the early solar system. Scientists measured the ratios of hydrogen to deuterium in the hydrated minerals, which acts like a fingerprint for water sources. The isotopic compositions revealed that water in the Bennu sample came from multiple sources during the asteroid's formation. Some water signatures matched those found in comets from the outer solar system, while others resembled water found in the inner solar system where Earth formed. This mixing indicated that water from different regions of the early solar system had combined within Bennu's parent body. The discovery of multiple types of hydrated minerals told different stories about Bennu's formation history. Serpentine minerals formed under relatively low temperature conditions when liquid water slowly altered olivine and pyroxene over millions of years. Magnetite formations indicated higher temperature hydrothermal processes where heated water circulated through rock fractures. Clay minerals showed evidence of surface weathering processes where water interacted with exposed rock surfaces. Each mineral type preserved information about different stages of water activity on Bennu's parent body. Water content varied dramatically between individual particles in the sample, revealing complex geological processes that operated within the asteroid. Some particles contained up to 20% water by weight locked within their mineral structures, while others showed minimal hydration. This variation suggested that different regions of Bennu's parent body experienced different degrees of water-rock interaction. Areas closer to the asteroid's interior may have retained liquid water longer due to radioactive heating, while surface regions cooled more quickly and preserved different hydration signatures. Scientists found particles containing water signatures that closely matched Earth's ocean composition. The deuterium to hydrogen ratios in these particles fell within the range measured in terrestrial seawater, supporting theories that asteroids delivered significant amounts of water to early Earth. This discovery strengthened the hypothesis that bombardment by water-rich asteroids during Earth's formation contributed to our planet's ocean formation. The match wasn't perfect, indicating that multiple sources contributed to Earth's water budget, but the similarity was close enough to confirm asteroids as major water delivery vehicles. Advanced spectroscopy techniques revealed how water molecules were locked within the crystal structures of various minerals. Infrared spectroscopy identified specific vibrational frequencies that corresponded to water molecules trapped in different mineral environments. Some water was chemically bonded as hydroxyl groups within crystal lattices, while other water existed as molecular water trapped in crystal defects and grain boundaries. The variety of water incorporation mechanisms indicated complex thermal and chemical processes that operated within Bennu's parent body over geological timescales. The findings suggested that Bennu's parent body had undergone extensive aqueous alteration billions of years ago. The degree of mineral alteration indicated that liquid water had persisted within the asteroid for millions of years, possibly tens of millions of years. This required internal heat sources to maintain liquid water temperatures in the cold environment of the outer solar system. Radioactive decay of aluminum-26 and other short-lived isotopes likely provided the necessary heating to sustain liquid water within the asteroid's interior during the early solar system. Samples revealed 11 evaporite minerals, halite, sylvite, trona, and abundant ammonia, confirming pockets of salty water on Bennu's parent body. These compounds form when water containing dissolved salts evaporates over extended periods, leaving behind crystalline deposits. The discovery of trona marked the first time this mineral had been identified in extraterrestrial samples. Trona forms in highly alkaline environments where sodium carbonate solutions evaporate, indicating that Bennu's parent body had developed extreme chemical conditions during water evaporation processes. The presence of abundant ammonia alongside these evaporite minerals provided additional evidence for ancient brine formation on the asteroid. Ammonia acts as an antifreeze in water solutions, allowing liquid water to persist at lower temperatures than pure water would permit. The combination of ammonia and dissolved salts created briny solutions that could remain liquid under the cold conditions of the outer solar system for extended periods. These brines concentrated dissolved materials as they evaporated, creating the diverse mineral assemblages found in the sample. These water-related discoveries indicated that the chemical building blocks necessary for life were likely widespread across the early solar system. The combination of liquid water, dissolved salts, and ammonia created environments where complex chemistry could occur. Objects that formed far from the sun carried these ingredients throughout the solar system, potentially seeding multiple worlds with the raw materials needed for life's emergence. The conditions preserved in Bennu samples suggested that similar processes operated on many asteroids during the solar system's formation. The water signatures represented just one component of Bennu's remarkable chemical complexity, but they provided the foundation for understanding how more organic compound revelations. Scientists identified over 100 distinct organic compounds using advanced analytical techniques that could detect molecular structures at incredibly precise levels. Among the most significant discoveries were 14 of the 20 amino acids that life on Earth uses to construct proteins, plus all 5 nucleobases that terrestrial life uses to store and transmit genetic information in DNA and RNA molecules. These weren't just simple carbon-based molecules. The sample contained complex organic structures that have preserved their molecular integrity for 4.5 billion years, providing an unprecedented window into the organic chemistry of the early solar system. The amino acid discoveries exceeded anything previously detected in meteorite samples. Scientists found these biological building blocks in concentrations hundreds of times higher than the best preserved meteorites in laboratory collections. The preservation was so exceptional that scientists could determine the exact molecular structures. These amino acids were found as a racemic mix, suggesting Earth's life chose left-handed later. Some particles contained amino acid concentrations that included extremely rare forms not commonly found in terrestrial environments. The nucleobases showed no signs of degradation despite spending billions of years exposed to cosmic radiation and temperature extremes. Finding these molecules in their pristine state within an asteroid sample provided direct evidence that the chemical building blocks for genetic systems existed in the early solar system before life emerged on Earth. The nucleobases carry genetic instructions, telling cells how to arrange amino acids into functional proteins, making their discovery crucial for understanding how biological complexity could emerge from asteroid materials. Scientists discovered organic compounds that had never been observed in any extraterrestrial sample before. These novel molecules included complex carbon structures with unusual bonding patterns and functional groups that don't occur naturally on Earth. Some compounds contained rare isotopic signatures that provided clues about their formation environments. The discovery of these unique molecules expanded the known inventory of organic chemistry in space and suggested that asteroid formation processes could produce molecular diversity far beyond what researchers had anticipated. The molecular structures showed remarkable preservation that defied expectations about organic compound stability over geological timescales. Amino acids and other biological molecules are typically fragile and decompose rapidly when exposed to heat, radiation, or chemical weathering. However, the Bennu samples contained organic compounds that had maintained their molecular integrity for billions of years. Scientists attributed this preservation to the protective environment within Bennu's parent body, where low temperatures and the absence of liquid water prevented chemical breakdown reactions. Some molecules appeared to be direct precursors to more complex biological compounds, suggesting active prebiotic chemistry on Bennu's parent body. Scientists found molecular fragments that could combine under the right conditions to form larger biological molecules like proteins and nucleic acids. These precursor compounds included simple peptides formed from linked amino acids and nucleotide-like structures that resembled the building blocks of RNA. The presence of these intermediate compounds indicated that chemical evolution toward biological complexity was already underway in the early solar system. Isotopic analysis provided crucial insights into where and when these organic compounds formed. Scientists measured carbon, nitrogen, and hydrogen isotope ratios that acted like fingerprints for different formation environments. Some compounds contained isotopic signatures matching those found in interstellar molecular clouds, indicating they formed in space before being incorporated into the asteroid. Other compounds showed isotopic patterns consistent with formation within the solar nebula or on the asteroid itself. These measurements revealed that organic molecules came from multiple sources across vast distances and timescales. High concentrations of ammonia throughout the sample provided insights into the formation environment of the organic compounds. Ammonia is highly volatile and typically escapes from warm environments, so its preservation indicated that many organic compounds formed in the cold outer regions of the solar system. The ammonia also served as a reactive component that could combine with formaldehyde, also detected in the samples, to produce amino acids and other biological molecules under appropriate conditions. These chemical pathways showed how simple inorganic molecules could evolve into complex organic structures. Scientists found clear evidence of organic synthesis reactions that had occurred within Bennu's parent body after its formation. Complex molecules showed chemical bonding patterns that could only form through specific reaction pathways requiring liquid water and moderate temperatures. Some compounds displayed isotopic fractionation patterns indicating they formed through enzymatic-like processes, though no actual enzymes were present. These synthesis reactions demonstrated that asteroids could function as natural laboratories for organic chemistry, producing biological molecules through purely geological processes. The distribution of organic compounds throughout the sample revealed complex mixing processes that operated within the asteroid. Different particles contained vastly different organic inventories, with some rich in amino acids, while others contained predominantly aromatic compounds. This uneven distribution indicated that organic molecules weren't uniformly mixed throughout the asteroid's parent body. Instead, different regions developed distinct organic chemistries based on local temperature, pressure, and water availability conditions. Advanced analytical techniques revealed that some organic compounds existed within mineral matrices that had protected them from degradation. Organic molecules were found trapped within crystal structures of silicate minerals, effectively sealed away from external chemical influences for billions of years. Other compounds were discovered within tiny fluid inclusions that preserved ancient chemical environments. These protective mechanisms explained how delicate biological molecules could survive the harsh conditions of space and the violent processes of asteroid formation. The organic compound discoveries provided the strongest evidence yet that chemical evolution toward biological complexity was widespread throughout the early solar system. The abundance and diversity of biological building blocks in the Bennu sample suggested that similar organic inventories existed on countless asteroids and comets. This widespread distribution increased the probability that life's raw materials were delivered to multiple worlds during the heavy bombardment period when asteroids frequently impacted planetary surfaces. Yet the organic molecules represented only one component of Bennu's remarkable chemical complexity. The mineral structures that had preserved these delicate compounds for billions of years held their own secrets about the asteroid's formation and evolution. Mineral composition surprises. The mineral analysis of Bennu's sample produced results that forced scientists to reconsider fundamental assumptions about asteroid classification systems. Traditional asteroid categories are based on spectroscopic observations from telescopes, which group asteroids by their surface mineral signatures. Bennu had been classified as a B-type asteroid based on these remote observations, suggesting a composition dominated by hydrated silicates and organic compounds. However, the detailed laboratory analysis revealed mineral diversity that extended far beyond any single classification category. Scientists found minerals characteristic of multiple asteroid types mixed together in individual particles, indicating that the current classification system oversimplifies the complex geological histories of these objects. Individual particles from the sample contained minerals that typically form under completely different temperature and pressure conditions, yet they were intimately mixed together as if they had formed in the same location. High-temperature minerals like olivine and pyroxene, which crystallize from molten rock at temperatures exceeding 1,000 degrees Celsius, were found alongside low-temperature clay minerals that form through aqueous alteration at temperatures below 100 degrees Celsius. This combination should be impossible based on current understanding of mineral formation processes. The mixing indicated that Bennu's parent body experienced multiple episodes of heating and cooling, with materials from different thermal environments becoming physically combined through unknown geological processes. Scientists discovered rare minerals that had never been observed in any meteorite sample previously studied on Earth. These novel minerals included complex phosphates, sulfates, and carbonate compounds with unusual crystal structures and chemical compositions. Unexpected magnesium-sodium phosphate crusts drew scientists to hypothesize Bennu came from a salty ocean world, suggesting liquid water throughout its early history. The presence of these unprecedented minerals expanded the known inventory of solar system chemistry and suggested that asteroid formation processes could produce mineral assemblages that don't occur naturally on Earth or in typical meteorites. The research team found traces of 11 minerals that form when water containing dissolved salts evaporates over extended periods, leaving behind crystallized salt deposits. These evaporite minerals are typically associated with dry lake beds and desert environments on Earth, where sodium-rich brines concentrate through evaporation. The discovery of such minerals in an asteroid sample indicated that Bennu's parent body had once contained bodies of liquid water with high concentrations of dissolved salts. The evaporation process that created these minerals required stable liquid water that persisted long enough for complete evaporation cycles to occur multiple times. Among the most significant discoveries was trona, a sodium carbonate mineral that had never been directly observed in any extraterrestrial sample before. Trona forms in highly alkaline environments where sodium carbonate solutions undergo repeated cycles of dissolution and precipitation. Its presence in the Bennu sample indicated extreme chemical conditions that are rare even in terrestrial environments. The mineral's crystal structure preserved information about the specific chemical composition of the brines that existed on Bennu's parent body, revealing pH levels and salt concentrations that provided insights into the asteroid's ancient aqueous environment. The mineral assemblages provided clear evidence that Bennu's parent body had experienced complex thermal and chemical evolution over geological timescales. Different particles contained mineral suites that formed during distinct evolutionary phases from initial accretion and heating through prolonged aqueous alteration and eventual cooling. Some minerals showed textural evidence of multiple recrystallization events, indicating that the parent body underwent repeated heating cycles. These thermal episodes were likely driven by radioactive decay of short-lived isotopes during the early solar system, followed by impact heating from collisions with other asteroids. Several minerals in the sample displayed characteristic features of shock metamorphism resulting from ancient impact events. Plagioclase feldspar grains contain parallel sets of microscopic fractures called planar deformation features that form only under extreme pressure conditions generated by high-velocity impacts. Olivine crystals showed evidence of pressure-induced phase transformations that occur when shock waves compress minerals beyond their normal stability limits. These shock features indicated that Bennu's parent body had experienced violent collisions with other asteroids, possibly including the catastrophic impact event that ultimately destroyed the parent body and created the debris field from which Bennu formed. The analysis revealed that different regions of the sample contained distinct mineral populations, indicating heterogeneous conditions within Bennu's parent body. Some particles were dominated by primitive minerals that preserved signatures of the original solar nebula, while others contained highly altered minerals that formed through extensive water-rock interactions. This heterogeneity suggested that the parent body had developed distinct geological zones with different thermal histories, water availability, and chemical conditions. The preservation of this diversity within individual particles indicated that the parent body's destruction and Bennu's subsequent formation had mixed materials from different zones. Crystalline structures within the minerals revealed detailed information about the cooling history of Bennu's parent body. Pyroxene crystals contained exsolution lamellae, which are microscopic intergrowths that form when minerals cool slowly from high temperatures over millions of years. The spacing and orientation of these lamellae provided precise temperature and cooling rate information, indicating that some regions of the parent body cooled gradually from initial formation temperatures. Other minerals showed rapid cooling textures that suggested exposure to space through impact excavation or surface processes. The mineral diversity discovered in the Bennu sample exceeded all computational models and theoretical predictions for asteroid composition. Current asteroid formation models assumed relatively simple mineral assemblages based on temperature zones within the solar nebula. The complex mixing of high-temperature and low-temperature minerals found in individual particles required more sophisticated models that could account for multiple formation and alteration processes. Scientists needed to develop new theoretical frameworks that could explain how such diverse materials became incorporated into single asteroid parent bodies. These mineral discoveries fundamentally changed scientists' understanding of asteroid formation and evolution processes. The unexpected diversity required updates to existing models of early solar system chemistry and dynamics. But beyond their geological significance, these mineral compositions held crucial information about Bennu's physical properties that would prove essential for understanding how external forces affect the asteroid's motion through space. Refined Yarkovsky Effect calculations. Lab-measured thermal properties showed Bennu radiates heat more slowly, deeper inside, and more quickly at the surface, strengthening the Yarkovsky thrust by 25% over previous estimates, which changes its orbit prediction. This non-gravitational force occurs when sunlight heats one side of a rotating asteroid, causing that heated surface to radiate infrared energy as the asteroid rotates and the surface cools. The radiation creates a tiny but persistent thrust that can gradually alter the asteroid's orbital path over millions of years. Previous calculations relied on theoretical estimates and remote observations, but the physical samples from Bennu provided direct measurements of the thermal properties that control how this effect operates. Laboratory measurements of thermal conductivity, heat capacity, and surface emissivity gave scientists the precise data needed to model how Bennu absorbs and releases solar energy. These measurements revealed fundamental properties that telescopic observations could never determine accurately. The thermal conductivity measurements showed how quickly heat moves through Bennu's surface materials, while heat capacity measurements indicated how much energy the surface can store before releasing it as infrared radiation. Surface emissivity measurements determined how efficiently different materials radiate heat back into space, which directly affects the magnitude of the Yarkovsky thrust. The analysis revealed that Bennu's surface has significantly lower thermal conductivity than scientists had estimated using remote sensing techniques. The measured thermal conductivity was approximately 40% lower than the values used in previous Yarkovsky effect calculations. This lower conductivity means that heat penetrates less deeply into the asteroid surface during daylight periods, creating steeper temperature gradients between the illuminated surface and the interior. The reduced heat penetration also means that surface materials cool more rapidly when they rotate into shadow, affecting the timing and intensity of infrared radiation release. Scientists discovered that surface composition varies dramatically across different regions of Bennu, creating complex patterns of heat retention and release that previous models had not accounted for. Some areas contain materials with high thermal inertia that store heat efficiently and release it slowly, while other regions have low thermal inertia materials that heat up quickly and cool down rapidly. These variations create local differences in the Yarkovsky effect strength across different parts of the asteroid surface. The compositional mapping showed that dark, carbon-rich regions behave differently from areas with higher concentrations of silicate minerals. The particle size distribution measurements from the sample analysis provided crucial information about surface roughness that affects heat distribution across Bennu's surface. Rougher surfaces create more complex thermal environments because shadows and surface angles affect how much solar energy different areas receive. Fine particles create smoother thermal gradients, while larger rocks and boulders create localized hot and cold spots that influence the overall radiation pattern. The sample analysis revealed that Bennu's surface contains a wide range of particle sizes, from microscopic dust to centimeter-sized fragments, creating a complex thermal landscape. The refined calculations demonstrated that the Yarkovsky effect on Bennu is approximately 25% stronger than initial predictions had suggested. This increase in strength means that the asteroid's orbital path will change more rapidly than previous models indicated, affecting the accuracy of long-term trajectory predictions. The stronger effect also means that Venus' orbit is more sensitive to small changes in thermal properties, making precise measurements even more important for accurate orbital forecasting. The increased strength of the effect compounds over time, so even small errors in early calculations can lead to significant uncertainties in long-term predictions. Surface roughness measurements revealed that heat distribution across Bennu is far more complex than smooth surface models had assumed. The asteroid's surface contains numerous boulders, ridges, and depressions that create intricate patterns of shadowing and thermal radiation. These surface features affect local temperature variations by up to 50 degrees Celsius, creating corresponding variations in infrared radiation intensity. The roughness effects are particularly important near Bennu's equatorial ridge, where large boulders create significant thermal heterogeneity that influences the global radiation pattern. Scientists found that seasonal variations in the Yarkovsky effect are much more pronounced than expected, driven by Bennu's orbital eccentricity and obliquity. As Bennu moves closer to and farther from the Sun during its orbital period, the intensity of solar heating changes significantly, affecting the strength of the thermal radiation thrust. The asteroid's tilted rotation axis also causes seasonal changes in which parts of the surface receive the most intense solar heating. These seasonal variations create periodic fluctuations in the Yarkovsky effect that must be accounted for in long-term orbital calculations. The thermal property measurements revealed that Bennu's surface materials have lower heat capacity than typical meteorite samples, meaning they heat up and cool down more rapidly than expected. This characteristic amplifies the Yarkovsky effect because it creates larger temperature differences between day and night sides of the asteroid. The rapid thermal cycling also means that surface materials experience more thermal stress, potentially affecting their physical properties over time. Understanding these thermal characteristics became crucial for predicting how the Yarkovsky effect might change as Bennu continues to orbit the Sun. These refinements have significantly improved the accuracy of long-term orbital predictions for Bennu, reducing uncertainty ranges in future position calculations by approximately 90%. The improved accuracy is particularly important for predicting Bennu's position during the 2135 Earth flyby, when gravitational interactions will significantly alter its subsequent trajectory. The enhanced models provide much more reliable estimates of where Bennu will be positioned relative to gravitational keyholes that could deflect it onto impact trajectories with Earth. This dramatic reduction in uncertainty has enabled scientists to develop far more sophisticated models for predicting exactly where Bennu will be when it encounters Earth's gravitational field in the next century. Updated 2135 trajectory projections. In 2025, supercomputers integrated all forces, including precise Yarkovsky data, narrowing Bennu's 2135 uncertainty zone to 50,000 kilometers. These simulations account for gravitational influences from all major planets, the gravitational pull from the largest asteroids in the main belt, solar radiation pressure, and the refined Yarkovsky effect calculations based on actual surface measurements. The computational models now process data at resolutions that were impossible when the OSIRIS-RX mission was first planned, creating trajectory predictions with unprecedented precision. The range of possible positions where Bennu could be located during its September 2135 approach has narrowed dramatically from the uncertainty ranges that existed before the sample analysis. Previous calculations suggested Bennu could pass anywhere within a region spanning several 100,000 kilometers during the flyby. The 2025 models have reduced this uncertainty zone to less than 50,000 kilometers, representing a 90% improvement in positional accuracy. This enhanced precision comes directly from incorporating the measured thermal properties of Bennu's surface materials rather than relying on theoretical estimates that introduce significant uncertainties into the calculations. The updated trajectory models reveal that Bennu will approach Earth more closely than earlier predictions indicated. The asteroid will pass within approximately 300,000 kilometers of Earth's surface, roughly 75,000 kilometers closer than previous calculations suggested. This closer approach results from the stronger Yarkovsky effect that scientists discovered through their analysis of the sample's thermal properties. The enhanced thermal modeling showed that Bennu radiates infrared energy more efficiently than expected, creating a larger thrust that has been gradually pushing the asteroid along its orbital path for millions of years. The probability calculations for gravitational keyhole encounters have undergone major revisions based on the improved trajectory modeling. Scientists have identified specific keyhole regions with much greater precision, calculating the exact coordinates where Earth's gravity could deflect Bennu onto dangerous trajectories. The 2025 models show that the probability of Bennu passing through any of the most concerning keyholes has decreased from earlier estimates. The closer approach distance actually works in Earth's favor because it moves Bennu's trajectory away from several keyhole regions that previous models indicated were at higher risk of encounter. Incorporating actual measured surface properties rather than theoretical estimates has eliminated major sources of uncertainty that plagued earlier trajectory calculations. The thermal conductivity, heat capacity, and surface roughness measurements obtained from laboratory analysis of the sample provided exact values for parameters that scientists previously had to estimate within broad ranges. These measurements revealed that Bennu's surface properties fall toward the extreme end of the ranges that scientists had considered. Plausible, explaining why earlier calculations contained such large uncertainty margins. The measured properties allowed researchers to eliminate dozens of possible thermal models and focus computational resources on the scenarios that match observed reality. Scientists discovered that Bennu's irregular shape contributes to orbital evolution in ways that spherical asteroid models had failed to capture. The asteroid's spinning top configuration creates asymmetric thermal radiation patterns that vary depending on which face receives the most solar heating during different parts of its orbit. The equatorial ridge that gives Bennu its distinctive shape affects how thermal energy distributes across the surface, creating complex radiation patterns that influence the Yarkovsky effect's direction and magnitude. Three-dimensional thermal modeling revealed that shape effects contribute approximately 15% of the total non-gravitational forces acting on the asteroid. The 2135 approach represents an unprecedented opportunity to validate these refined prediction models through direct observation. Ground-based telescopes and space-based observatories will track Bennu's position with extraordinary precision during the flyby, measuring its exact trajectory and comparing it to the 2025 computational predictions. This real-time validation will test not only the accuracy of current models, but also the reliability of the thermal property measurements and computational methods that produce them. The encounter will provide the most rigorous test ever conducted of asteroid trajectory prediction capabilities. Multiple independent research teams using different computational approaches have confirmed the updated trajectory calculations, lending confidence to the results. Teams at NASA's Jet Propulsion Laboratory, the European Space Agency, and universities in Japan and Italy have all produced similar results using their own modeling techniques and computational resources. The consistency across different research groups eliminates concerns about systematic errors in any single modeling approach. Cross-validation between teams revealed minor differences in specific details, but all groups agree on the fundamental conclusions about Bennu's 2135 trajectory. Seasonal variations in solar radiation intensity affect Bennu's thermal properties throughout its orbital period, creating periodic changes in the Yarkovsky effect that previous models had simplified or ignored. The asteroid receives 20% more solar energy at perihelion than at aphelion, causing corresponding changes in surface temperature and infrared radiation patterns. The 2025 models simulate these thermal cycles in detail, calculating how seasonal heating variations affect the cumulative orbital drift over multiple orbital periods. This level of detail required tracking Bennu's thermal state through hundreds of individual orbital cycles to capture the long-term average effects. The improved accuracy and trajectory prediction provides scientists with much greater confidence when assessing Bennu's long-term impact risks for time periods extending well beyond the 2135 encounter. Previous uncertainty ranges were so large that impact probability calculations remained highly speculative for encounters in the 22nd and 23rd centuries. The refined models enable meaningful risk assessments for specific future time periods, allowing planetary defense planners to prioritize monitoring and mitigation strategies based on quantitative threat analysis rather than broad estimates. These enhanced trajectory calculations have fundamentally changed how scientists approach the critical question of where exactly Bennu. Gravitational keyhole analysis. Using our precise models, we mapped 78 keyholes, cosmic pinball zones where Earth's gravity could send Bennu on a collision course. Only a dozen of these carry any real impact risk. These keyholes function like cosmic pinball bumpers. If Bennu passes through one of these precisely defined zones during its 2135 flyby, Earth's gravitational field will bend the asteroid's path in exactly the right way to bring it back for a potential impact during a future orbital pass. The 2025 computational models have mapped these keyhole locations with extraordinary precision, identifying their exact coordinates and dimensions with accuracy that was impossible using earlier calculation methods. Each keyhole has been mapped as a three-dimensional volume in space, with specific entry and exit points that correspond to different impact scenarios. The largest keyhole measures approximately 2,400 kilometers in width, while the smallest measures just 180 kilometers across. The size variations reflect different deflection angles that would result from passages through each zone, with larger keyholes corresponding to more dramatic trajectory changes. The probability calculations for Bennu encountering any of these dangerous keyholes have undergone major revisions using the updated trajectory data. Previous estimates suggested a combined probability of approximately 1 in 2,700 for passage through any impact causing keyhole. The 2025 calculations have reduced this probability to approximately 1 in 4,200, representing a significant decrease in assessed risk. This improvement stems from the more accurate trajectory predictions that position Bennu's 2135 flyby path away from several keyhole regions that earlier models had identified as potential encounter zones. Advanced gravitational modeling techniques can now simulate Earth's gravitational effects on Bennu with computational precision that exceeds previous capabilities by several orders of magnitude. The models divide Earth's gravitational field into millions of discrete calculation points, accounting for variations in gravitational strength that result from Earth's rotation and perturbations from other celestial bodies. These simulations can predict gravitational deflections accurate to within meters over the duration of Bennu's flyby period, compared to earlier models that contained uncertainties of several kilometers. The analysis revealed that Earth's gravitational field could deflect Bennu in 47 different directions, depending on which keyhole the asteroid might encounter. Each deflection scenario produces a unique post-Flyby trajectory that determines when and where Bennu might return for subsequent Earth encounters. Some deflections would send Bennu on elliptical orbits that bring it back to Earth's vicinity within 50 years, while others would alter its path so dramatically that future encounters become impossible for centuries. The most extreme deflection scenarios could eject Bennu from its current orbital zone entirely, sending it toward the inner or outer solar system. Scientists discovered that the precise timing of Bennu's 2035 approach critically affects which keyholes become accessible during the flyby period. The asteroid's approach trajectory intersects different keyhole regions depending on arrival time variations of just a few hours. Morning arrival times position Bennu's path through different gravitational zones than afternoon arrivals, even though the overall flyby distance remains similar. This timing sensitivity means that small uncertainties in Bennu approach schedule translate into different sets of potential keyhole encounters, requiring scientists to model multiple temporal scenarios. The updated calculations demonstrate that most keyhole passage scenarios result in trajectory changes that move Bennu away from future Earth collision paths rather than toward them. Of the 78 identified keyholes, only 12 would deflect Bennu onto trajectories that could result in Earth impacts during subsequent orbital periods. The remaining 66 keyholes would bend Bennu's path in directions that eliminate future collision possibilities or delay potential encounters by centuries. This finding significantly reduces the practical impact risk compared to earlier assessments that assumed more keyholes posed serious threats. Researchers can now predict the specific orbital modifications that would result from passage through each individual keyhole region. The calculations show that Keyhole 3, the largest identified zone, would increase Bennu's orbital period by approximately 8.3 months and shift its trajectory by 2.7 degrees, creating a potential Earth encounter in 2187. Keyhole 27 would decrease the orbital period by 3.1 months while deflecting the trajectory by 1.4 degrees, setting up a possible impact scenario in 2196. These precise predictions allow scientists to assess the relative dangers posed by different keyhole encounters. Scientists have identified correlation patterns between keyhole encounters and long-term orbital stability that affect Bennu's evolution over multiple centuries. Passage through certain keyholes would place Bennu into orbital resonances with Earth that create periodic close approaches every few decades. Other keyhole passages would break Bennu free from its current orbital pattern, sending it into chaotic trajectories that make long-term prediction impossible beyond 2200. Understanding these stability patterns helps scientists assess which keyhole scenarios pose the greatest long-term threats to Earth. The keyhole mapping represents a fundamental breakthrough in asteroid threat assessment, providing scientists with the precise data needed to evaluate specific impact scenarios rather than relying on broad statistical estimates. The enhanced understanding of these gravitational zones allows researchers to identify exactly which trajectory changes pose real dangers and which represent false alarms. This level of precision transforms how scientists approach the broader question of assessing Bennu's long-term threat to our planet. Long-term impact risk assessment. The comprehensive data from the 2025 Bennu sample analysis has produced the most detailed impact risk assessment ever conducted for any asteroid. Scientists can now calculate precise impact probabilities for specific decades within the 22nd and 23rd centuries rather than providing broad estimates across multiple centuries. The enhanced computational models process millions of trajectory scenarios that account for every known force acting on Bennu over the next 300 years. These calculations incorporate gravitational influences from all planets, radiation pressure from the sun, the refined Yarkovsky Effect measurements, and complex interactions during multiple future Earth encounters. The updated models reveal that Bennu poses a 1 in 1,750 chance of impacting Earth between now and the year 2300, now 0.057% versus earlier 0.05%. Still tiny, but slightly worse than before. The increase comes from the more accurate Yarkovsky Effect calculations based on measured thermal properties rather than theoretical estimates. The stronger thermal thrust identified through sample analysis means Bennu's orbital evolution proceeds more rapidly than earlier models predicted, bringing potential impact scenarios forward in time and increasing their cumulative probability over the assessment period. Scientists have identified September 24, 2018 as the single most likely impact date with a probability of 1 in 2,700 or approximately 0.037%. This specific date emerges from detailed modeling of how gravitational keyhole passages during the 2135 encounter could deflect Bennu onto collision trajectories. The 2182 scenario requires Bennu to pass through Keyhole 3 during its 2135 flyby, which would alter its orbital period by exactly the amount needed to bring it back to Earth 47 years later. The precision of this calculation demonstrates how advanced modeling techniques can identify specific threat windows decades in advance. Multiple scenario analyses have examined how different keyhole encounters during the 2135 flyby would affect Bennu's subsequent orbital evolution. The computational models simulate 47 different deflection scenarios corresponding to passage through various gravitational keyholes. Each scenario produces a unique post-2135 trajectory that determines when and where Bennu might return for future Earth encounters. The scenario modeling reveals that 78% of possible keyhole passages would actually reduce long-term impact risks by deflecting Bennu away from future collision trajectories. The assessment incorporates detailed modeling of how gravitational interactions during multiple future close encounters would compound over time to affect impact probabilities. Beyond the critical 2135 flyby, Bennu will experience additional close approaches to Earth in 2196, 2218, and 2251. Each encounter presents opportunities for further gravitational deflections that could either increase or decrease future impact risks depending on Bennu's trajectory at the time. The models simulate these cascading gravitational effects across multiple orbital periods to calculate cumulative impact probabilities. Scientists have identified 3 main risk windows when impacts become possible if specific gravitational deflection scenarios occur. The highest risk period extends from 2180 to 2190, when 7 different impact scenarios could occur depending on keyhole passages during earlier encounters. A secondary risk period spans 2225 to 2145, corresponding to impact scenarios that require multiple gravitational deflections across several Earth encounters. The tertiary risk period covers 2275 to 2290, representing the latest possible impact dates that current models can predict with meaningful accuracy. Advanced statistical techniques provide probability ranges with confidence intervals that quantify the reliability of long-term predictions. The 1 in 1,750 overall impact probability carries a 95% confidence interval ranging from 1 in 1,200 to 1 in 2,500. This range reflects uncertainties in modeling complex gravitational interactions and non-gravitational forces over century-long time periods. The confidence intervals narrow significantly for nearer-term predictions and widen for scenarios extending beyond 2250, when small modeling uncertainties accumulate into larger prediction errors. The risk assessment methodology considers not just direct impact scenarios, but also near-miss encounters that could set up future collision trajectories. Some gravitational deflection scenarios place Bennu into orbital resonances with Earth that create periodic close approaches every few decades. These resonant orbits increase the number of opportunities for future gravitational deflections that could eventually result in impacts. The models track these multi-step scenarios across several orbital cycles to assess their contribution to overall impact risk. If Bennu struck in 2182, energy equivalent to 1,200 megatons would devastate a 6-mile-wide crater. This scenario involves a shallow-angle collision in the Pacific Ocean that would release energy far exceeding any nuclear weapon ever detonated. The impact would create tsunami waves that could affect coastlines across the Pacific Basin, while atmospheric effects could influence global climate patterns for several years following the collision. The findings demonstrate that overall impact risk decreases substantially compared to some earlier estimates that suggested higher probabilities based on less precise orbital calculations. Previous assessments using theoretical thermal properties had suggested impact probabilities as high as 1 in 1/500, while sample-based calculations indicate 1 in 1,750. This improvement results from more accurate trajectory predictions that position Bennu's future encounters away from several gravitational keyholes that earlier models had identified as higher risk zones. The assessment includes modeling of how measurement uncertainties in current orbital data propagate into long-term prediction errors. Small uncertainties in Bennu's current position and velocity measurements create larger uncertainties in predicted positions decades into the future. The models quantify how these uncertainties affect impact probability calculations and identify which measurements would most improve prediction accuracy. Additional radar observations of Bennu over the next decade could reduce uncertainty ranges by approximately 40%. These findings will guide planetary defense priorities and resource allocation decisions for monitoring potentially hazardous asteroids. The detailed impact timeline enables space agencies to plan observation campaigns and potential deflection missions with specific target dates and scenarios in mind. The assessment methodology developed for Bennu establishes frameworks that can be applied to other potentially hazardous asteroids to create comprehensive threat catalogs for planetary defense planning. The 2025 risk assessment represents the most thorough analysis of any single asteroid's threat potential ever conducted, establishing new standards for impact hazard evaluation. The integration of physical sample data with advanced computational modeling has produced impact probability calculations with unprecedented accuracy and detail. These results demonstrate that sample return missions provide crucial data for planetary defense applications beyond their primary scientific objectives, making them valuable investments in protecting our planet. The discoveries emerging from this comprehensive analysis have fundamentally changed how scientists understand both the nature of asteroids and the methods needed to study them. These breakthroughs establish new benchmarks for planetary science research and asteroid threat assessment capabilities. In 2025, lab analysis of Bennu's sample unveiled complex organics and unexpected minerals, revealed water history, and laser-sharp orbit predictions that changed impact odds to 1 in 1/7,5, spotlighting September 24, 2182 as the prime impact date if a keyhole passage occurs. The discovery of 14 amino acids and all 5 nucleobases confirmed that asteroids delivered life's building blocks throughout the early solar system. Water signatures and evaporite minerals demonstrated that Bennu's parent body hosted liquid water for millions of years. The 90% reduction in orbital uncertainty transformed vague statistical estimates into precise trajectory forecasts that identify specific threat windows decades in advance. These findings demonstrate how sample return missions provide data that telescopic observations alone cannot deliver, establishing new standards for understanding potentially hazardous asteroids and developing effective plans